Hello everyone, my name is Saman Dehghan and welcome to my presentation Application of AI-based modeling and prediction to reverse osmosis desalination plant. During this presentation, we will cover the overview of our system, motivation and problem formulation, status of the current project and future work. Water scarcity, which results from a mismatch between water resources and water demands, is not limited to arid areas. The water quality has decreased in many regions due to the pollution and exploitation of groundwater and surface water. Furthermore, the growth of the population leads to an increase in water demand for the industry and agriculture. As a result, exploring an alternative resource for fresh water has gained many interest. Desalination is the answer to this, such as alternative resources. Desalination systems are divided into two main groups based on the separation process. Thermal desalination exploits evaporation and condensation to separate solid material from water. The other separation process is the membrane desalination technique. RO is the most popular technique in which water diffuses through the membrane and it retains solid particles. This figure demonstrates the process of water desalination using RO, which include three stages, such as pre-treatment, RO system, and post-treatment. We focus on the main RO system for modeling. Our aim here is to design a most accurate model to be used in the future as a base model for the optimizer to find a profile of optimal set point of the plant. Here in this table, you can see some relationship among RO variables which can be used as a feature engineering to enhance the model reliability. Here we define two types of feature that can be extracted from mathematical description. First, those can be calculated directly based on the inlet variables. Also, there is a more complex type that there is no direct relationship with inlet variables. However, they are described based on the inlet and outlet variables. And in this project, we're going to estimate those type of variables and add more advanced feature extracting to increase the model accuracy. Although model-based or data-driven approach can model the RO process with acceptable accuracy, our intention here is to find the most accurate model that combines the benefit of two approaches. The quality of mathematical description of RO is highly depends on the membrane properties, which can be deteriorated over time. So incorporating expert knowledge into deep neural network addresses some of the bottlenecks, such as reliability, faster convergence, and limited training data. But it can introduce new issue, which can be error propagation through neural network. We propose uncertainty structure for the neural network model to predict the mean and variance of the output instead of the point prediction. It doubles the size of the output, however, gives us the uncertainty related to the input noise. Furthermore, as there is a dropout layer in the training step, we applied bootstrapping method to estimate the model uncertainty by activating the dropout during the test step. The main reason to design this structure has been shown in the left figure. Our goal is to update the dropout mask which is applied on the augmented training data when we combine all extracted features with inlet variables to predict outlet variables. We modify the update rule of the dropout mask to eliminate those samples from the augmented data with high predicted variance. The top table shows inlet, outlet, and two types of intermediate states variable. The first type that can be calculated using inlet condition, and the second type needs to be estimated. Inlet variables including feed flow, brine valve position, feed temperature, feed salinity, and calculated feature are feed osmotic pressure, temperature correction factor, and estimated feature is water permeability, and the outlet variable is our feed pressure and permeate salinity. And the detail of the feed-forward neural network model brought in this table. We also compared the proposed framework with numerous deep learning techniques as it's shown in the figures. Mean percentage error has been improved using hybrid structure and deterministic dropout. Also, we introduced new measure, that is the percentage of the sample that has the mean percentage error over 10%. It reveals that using deterministic dropout has great impact to introduce the percentage of large error for permeate salinity. Finally,
It's the future work that we're going to design Optimum to find the profile of optimal set point, also using the mixture density network to estimate the uncertainty, because it can cover the system that does not follow any parametric distribution. Thank you.